Hey, good evening. You are welcome to A-selim simulation. So we'll be spending few minutes together. So today I'm going to solve a problem on structural analysis, static structural analysis. The problem is to analyze the hydrostatic pressure on water tank. This is a problem given to us by our professor. So I'm a student of Mechanical Engineering Department, final year, University of Ibadan, Nigeria. So this is the program was given to us by Professor Oho Oluwole, the course facilitator. The program goes us we are to simulate the hydrostatic pressure of water tank with a diameter of 1,700 millimeter, thickness of 8 millimeter, which is standard thickness for 4,500 liter tank, and water height inside the tank is 2,100 millimeter, which is 2.1 meter. So and the material is HDPE, high density polyethylene. So I will start from this is the workbench of ANSYS. So and then I assume that the listener will have already known how to use CAD software to draw water tank. So what I gave was the dimensions of the tank. So we give the static structure. I left click and drag to this. So uh, this window pop up. Double click on the engineering data. So since the material we are given is high density polyethylene, I'm not really sure if we have that already in analysis, but I can just create it because I have all the property of that. I can just create it HDPE, enter. So the material has been created, and I will have to come to the property linear elastic. Under this linear elastic, click the drop down, the drop plus sign, this isotropic elasticity. Left click, drag and drop to the ADP. You can see that once I dropped it, all these properties shown on my screen. But some material, some property is still missing, like density, yield. So I can go to feed variable again. I'm sorry, ADP again. I go to that ADP. You can see under physical property, this is density. I drop that density. So density that I shown here, I'll still go again, look for strength. This is the drop down. Click on the strength. Tensile strength. I left click, drag and drop. I have tensile ultimate strength. Left click, drag and drop. So all the material I have every property here now. So now I can type in the value density. My density is in kilogram per meter cube. The value of density is 952 kilogram per meter cube. I have long modulus which is elastic modulus. I change the unit to MPa, that is megapascal. I enter the value which is 106 CV dot 8 Poisson ratio. I enter the value which is 0.40 0.4 I'm sorry 0.4101. Yes, I enter. Once I enter, bulk modulus, shear modulus, everything updated. So I now go to tensile strength. The tensile yield strength here is tensile yield is 20 MPa. I change the unit to MPa. I enter the value 20. Enter tensile ultimate strength. I change the unit to MPa. I enter the value 22.1 MPa. Enter. So I've entered all the properties, and now I can move to the project. This project, click on the project, now back to the project. You can see the step 3 now is geometry. I right click on the geometry, import geometry. I browse. Now I now go and pick the design, the time that I've already moved on SolidWorks. This is hydrostatic. I'm sorry about the spelling, I made a mistake by typing. So hydrostatic pressure tank. I open that. So go to model, double click. You can see set starting mechanical. Mechanical is starting now. So let's put a minute for the mechanical window to pop up. So it's another interface. So you can see it's already coming. So it's even less than a minute. Let's just give it like few seconds for mechanical to pop up. Yes, we have mechanical already. So let's avoid the geometry. These are geometry. Let's avoid it. Yes, these are tank. This is the tank. We have the tank already. Now I'll go to the geometry, click on the geometry import. You can see material assignments. Under the material assignments, I think from by default, ANSYS is going to assign it, it's going to treat it as a structural steel, which is like my steel. So I click on the structural steel, this drop down, I click on it, change it to the material that I included. So I've already assigned that material. So you can check HDPE. So close it out and now come to mesh. So in this mesh, another way to waste time, this might be the video for another time. So I'm inside the method. I want my method to be applied to all the geometry. I right click on the where graphics window, select all. I click on now apply now. So method, I want tetrahedron meshing. So another video will come up on meshing. So let's go ahead and say let's apply. Now since we are dealing with hydrostatic pressure and there is no that govern that pressure increase with depth, definitely we are going to have the stress is going to concentrate at the bottom. So with that, I'm going to refine the mesh near the bottom to capture the real essence of the analysis, like to capture the stress, strain, or the analysis that we want to do. I will refine the mesh at the near bottom. So as I said, another video will be on that. We just follow up on this and inside sizing. So now sizing, I pick the face selection. Now mirror this, go to the inside. I click on this, hold the control key, and then I select this near bottom inside face because the water is going to turn the inside face, not the outside, and the bottom part is going to be fixed. So I don't really need to do that. I apply, and then let me change the unit to millimeter first. Yes, apply element size. Let me give it 13, and then that's local sizing. I'll come to global that sizing. Let me give this one 150. Yes. Now let's mesh. Come to mesh, right click, generate mesh. This might take a minute or two. So let's look at the mesh. It might take a minute or two. So look at the geometry, you can see that it's already discretizing it. So the purpose of the mesh is to discretize this entire cylinder. So that the hydrostatic fluid will now act on each element and discretizing into smaller elements. So based on the value that I give this to, and mind you, I can actually discretize everything to be 15, but since I'm using student fashion, so I have limited number of nodes and elements that I can use. So for student fashion, it's 128 nodes, and I don't want to exceed that. Yes, you can see amazing. Let's check the inside. That is where the main of interest. You can see I have final mesh inside. So let's go to mesh to check the mesh. First, I will check the statistics log. If I've not exceed the student version, so I have 11,000 plus, and the maximum threshold is 128. So we are fine. We are good to go. So now, before we proceed, I would like to check the quality of my mesh. I'll come to mesh quality, then mesh metric. Under this node, I'm going to verify two properties here: element quality. So this window pop up, and then I'm going to check my element quality. So let me first check this one: 0.75. Let's see where it's for. Yes, it's actually a fault to where I define. And let me check this one: 0.94. It's actually 4 where I define. So let me check another property: skewness. Yes, skewness. Let me start from this and see where it's for. It's 4 where I define. So the purpose of this element quality is that you should target element quality closer to mark. But for academic purpose and undergraduate study, so from 0.7 to 1 is acceptable. It's good. For skewness, you have to target 0, but between 0.5 to 0 is okay. So you can see that where the stress is going to concentrate, as I've already defined that place, and then the skewness and the element quality behind that place is very fine. So we are good to go now. Now that the mess is fine, we are going to the static structural. I'll click on the static structural, insert, go to fix support. Fix support. We are fixing the bottom part. Apply. Once we fix the bottom part, I still go back to static structural, right click, insert. What are we inserting now? Standard gravity. Since we are dealing with water, I mean fluid, hydrostatic. So the gravity is going to act downward. So I've inserted the gravity. So let me change the unit first so that fine. I change to meter kilogram unit. So you can see the gravity is acting in Z direction, which is wrong. Want it in the, let me put to position y direction. So change the direction from here to negative y to act downward. So we are good now. The gravity is acting downward. So again, I will insert the hydrostatic pressure here. So the pressure is acting inside the tank. So I will have to select all the faces inside the tank, zoom in so that I can be able to capture the inside of the tank. I click here, hold, click, click, click. Yes. I think I'll be able to select everything. Yes, yes. That's been highlighted. I've selected all the inside of the tank and then I'll click on apply. So when I click on that, you can see that we have fluid density. The density of the fluid now is on which fluid are we dealing with? We're dealing with water. It's 1000, 1000. Unit matters here. 1000 kilogram per meter cube. You must follow the unit. The 1000 meter per kilogram per meter cube. Now, hydrostatic acceleration. So I'll change the vector to components and it's acting in what component, what direction. It's going to have the same value as gravity for the direction. What since gravity is acting downward, acceleration will be acting upward. That will be 9.8. The same magnitude for different direction. So now we still move down. We have free surface location. The free surface location is acting well like where is the level of the water? And from our problem statement, the level of water was, I mean, if the level of water given was 2,100 milliliter, which is 2.1 meter, I would write 2.1 meter. Yes, you can see that the surface has moved. You can see everything now. So, yeah, we've applied that. So now, what do we need to solve? We need to solve for, we come to solutions, insert, we need stress, which is equivalent for minus stress. Again, we insert strain, which is equivalent for minus strain. Again, we insert deformation, directional deformation in what axis? Y axis. And then we insert stress to maximum equivalent stress. This is well our factor of safety. This is all we are asked to do. So now we can solve. So it's going to take 2 to 3 minutes at max. So let's have the solution. Let's wait for the solution. It's coming. Let's wait for it. Yes. The next few seconds. So have our solution. Yes, it's completing the solution already. Yes, we are fine. So let's check our equivalent for night stress. This is in Pascal. Let me change the unit to meter so we can see 4.64 MPa. That's the maximum equivalent stress. Equivalent strain, directional deformation, factor of safety is 4, minimum factor of safety is 4.60, which is really safe. You can come here, equivalent stress. If you want to see how the thing is Yes, click on this. You see how the stress is distributed, and then if you want to scale, you can come here, display, and start to insert scale, through scale. This is it. We have maximum stress at the bottom and the minimum here. Let's check to strain. The same thing as strain. Directional deformation is still at the bottom. Factor of safety, the minimum factor of safety is at the bottom because the pressure in the bottom that we have the highest load. So now you can probe at different locations to check factor of safety or anything you can probe. So now let's go back to room. We are done with the analysis. This how to generate reports. Come to the report preview or print preview. This is how the report is going to look like. I mean, the print is going to look like. You just want to print some pages. Report preview. This is a report. ANSYS is generating the report. This is a report. You don't have to type anything. ANSYS will automatically generate all the reports. So, and once it's done, you can come to print. This is print sign. Then Microsoft into if you want it in PDF or OneDrive desktop, anything you want, then print it. Okay. This is all for today. Thanks for your time.